Hi, this is Mr. Mack. We want to talk today about solving systems of simultaneous linear equations in 3 variables. Now, before we actually start on the procedure of solving them, let's talk for a moment or two about what they mean. A linear equation in 3 variables might be something like 3x plus 2y plus 4z equals 12. Now, an equation in 2 variables, a linear equation in 2 variables, actually represents a line in a plane. A linear equation in 3 variables represents a plane in space. In other words, lines are, one dimension less than a plane, and so an equation in 2 variables is a line in a plane. And then since planes are 2-dimensional objects and space is 3-dimensional, linear equations in 3 variables represent planes in space. Now, it turns out that if you have 2 planes in space and they intersect, their intersection will be a line. If you think about it, hold up 2 sheets of paper that aren't parallel, and if you kind of bring them together, you'll see that there's a line where they kind of come together. Now, if you wanted a single point in space, you would need a 3rd plane that wasn't parallel to either of those 2 planes to actually intersect that intersection of the other 2, and you would finally get a point. So it turns out that what you need in to get a solution to an equation of 3 variables is you actually need 3 equations. You need 3 planes to determine a single point. Now, just as the 2 variable systems, that won't always happen. Sometimes you'll have 3 variable systems that will generate infinitely many solutions, and sometimes you'll have 3 variable systems that generate no solutions. And we'll talk about how that happens in a couple of minutes. But to start off with, if you're going to have a single point solution to linear equations with 3 variables, you're going to need 3 equations. And generally, we can add a 4th variable and a 5th variable and so forth like that. Generally, if the equations are linear, you're going to need as many equations as you have variables. Now, let's take a look at the method that you would use to solve a system of simultaneous linear equations. Let's imagine we have the system x plus 2y plus 3z is equal to let's go with 14. And then let's say we have 3x minus y plus z equals, well, what does it equal? 4. And let's have a 3rd one here. 2x plus 5y minus 3z is going to be equal to 3. Okay. Now, if this is our system of simultaneous linear equations, then what we want to do is we want to solve this system, and we want to know what number for x, what number for y, and what number for z makes all 3 of these equations true at the same time. Now, the method we're going to use is very like elimination for 2 variables. But now there's a couple of things that I really want to emphasize here. First of all, you must use each of the equations at least once in eliminating a variable. Okay, so for example, if I chose to eliminate the variable x using equations 1 and 2, I would have to go back again and eliminate x. And the second time, I would have to use equation 3. Now, it wouldn't really matter which other equation I used, but each equation must be used at least once. If you don't, you will be led to some false conclusions. Now, the second thing that I would emphasize here is when you're doing this and you're eliminating the first variable, either x, y, or z, or whatever letter it is that the equations are in, you must make sure that you eliminate the same variable twice. If you take equations 1 and 3 and eliminate x, and then you take equations 1 and 2 and eliminate y, then if you take those two equations and eliminate z, you'll get back to x and y, and you'll find yourself traveling around and around in circles. So it is extremely important when you're doing one of these problems through elimination that before you start, you plan ahead and you look and you say to yourself, which variable is going to be easiest for me to get rid of twice? Okay, because you've got to get rid of the same variable twice, and each equation has to be used at least one time. Now, with this system right here, it could very well be that the easiest equation, the easiest variable to get rid of twice would be z. Because if you notice, if you added equations 1 and 3 together, z would go away. Now, we would have to go back and use equation 2 to get rid of z again, but that's not that bad, because in equation 2, z only has a coefficient of 1. So let's do that. First of all, we'll get rid of z using equations 1 and 3. So what I'm going to do is I'm going to add x plus 2y plus 3z equals 14 to the equation 2x plus 5y minus 3z is equal to 3. When I do, I get 3x plus 7y, and the z's go away, equals 17. Now, I'm going to call this equation 4. Notice I'm actually circling the numbers for the names of the equations. Now, I got that equation using equations 1 and 3. So I must now get rid of z, same variable, got to get rid of the same variable, and equation 2 has to be one of the ones I'm going to use. Now, if you look at it, I could use either equation 1 or 3. I'm going to choose to use equations 2 and equation 3. Because if I multiply equation 2 by 3, I get 9x minus 3y plus 3z equals 12. And equation 3 can just be written as it is, 2x plus 5y minus 3z equals 3. I'll get the equation 11x plus 2y equals 15. Now, I'm going to call this equation 5. Equations 4 and 5 now form a system of two equations in two variables. So I have 3x plus 7y equals 17, and I have 11x plus 2y equals 15. Now, this is a system of two equations in two variables. Now, the x number and the y number of this system that make this system true are the x number and y number of the big system that makes it true, although z has been eliminated. So now, to get rid of a variable, this is, okay. Well, let's multiply the first equation by 2. That gives us 6x plus 14y equals 34. And we'll multiply this second equation by negative 7. That gives us negative 77x minus 14y equals, now 15 times negative 7. That's negative 70 plus negative 35. That's negative 105. Now, if I add these together, I get negative 71x equals, whoa, look at that, negative 71. That was nice. So if I divide both sides by negative 71, I get x equals 1. Now, we're certainly not finished. We're not even close to being finished. We've got a long way to go here, but we do have a significant in-row to this. Now, if we haven't made any mistakes along the way, every equation that we've written, one will be a solution to that system. So what I can do is I can put one back in any equation here to get another variable. And equations 4 and 5 are the ones that are kind of asking to help out. So let's do this. Let's put 1 in equation 4 for x. I get 3 times 1 plus 7y equals 17. Subtracting 3 from both sides, I get 7y equals 14, which gives me y equals 2. That was nice. Now, I'm going to put x and y back in an equation to find z. And we may as well use equation 1. So I get x, which we found to be 1, plus 2y, which we found to be 2, plus 3z equals 14. So 1 plus 4 is 5. 5 plus 3z equals 14. Subtract 5 from both sides. 3z equals 9, so z equals 3. So now, we use equation number 1 to find the third variable. So it's important for us to check that ordered triple in equations 2 and 3. So if we put 1 in for x, and 2 in for y, and 3 in for z, 3 times 1 is 3, minus 2 plus 3, we get 3 minus 2 is 1, plus 3 is 4. That one checks. Now, 2 times 1 is 2, 5 times 2 is 10, 3 times 3 is negative 9. We get 2 plus 10 is 12, minus 9, that's 3. That one checks as well. So we have checked this system now, and we can now report that our solution is the ordered triple 1, 2, 3. Now, a couple of things. First of all, if you're doing an algebraic solution to a system of 3 equations and 3 variables, there will either be 1 point, like we got in this particular case, or there will be no solutions. In other words, if the equations name parallel planes, for example, there would be no solution. There can actually be a couple of other things that would happen too. But we might have no solutions, or we might have infinitely many solutions. Now, there are examples of each of those situations in the solution problems that you're going to be viewing. So I will simply say this. What happens in those two cases when you have infinitely many solutions or no solutions? If you have infinitely many solutions, when you try to get rid of the second variable, the third variable will go away also, and you will get a true equation like 5 equals 5. In other words, it will be true. Now, no variable appears in this equation, but it's always true. That means that there will be infinitely many solutions. And there is an additional step that I'm going to show you in the solution videos as how to describe the solutions to a system that has infinitely many solutions when you've got 3 variables. And so you'll have to watch the videos to see that. The other thing that can happen is you can get no solutions. Now, no solutions occurs when the third variable goes away at the same time the second variable goes away, and you get an equation like 0 equals 5. Now, this equation is always false. It does not matter what x is. 0 will never be equal to 5, so there will be no solution. So when you get an equation with no variables that's true, you have infinitely many solutions. When you get an equation with no variables that's false, you have no solutions. One thing you do have to remember, though, if you got this equation that was true and you didn't use all of your equations, That is a problem. You must use each equation of the three original ones you're given at least once. If you don't, you may get this 5 equals 5 or 0 equals 0, but what you did was you substituted something back into itself and you're not actually solving the system. So, was there something else that needed to be said? Let's just revamp quickly. When you have a system of three equations and three variables, spend a moment looking at the original system first and decide which variable you want to get rid of twice. It's got to be the same variable, and you've got to use each equation in that method at least once in getting rid of the variable twice. Then the two equations you get after having gotten rid of the variable twice form a system of two equations in two variables that you then solve and then back substitute and check your solution in all of the equations you didn't use to get the third value. And that is solving systems of three equations in three variables. We're done.